No. Oh my gosh. She's a functional athlete.
Okay, well, it's officially time to start. Welcome. Surviving the cold and the wind chill. There's even people that made it to lab this morning, so that was good. Do you have any questions? Okay, so we need to review a few equations, right? Impulse momentum, what is impulse equal to? How do we calculate an impulse? Yes, so we have a net amount of force that is applied over a period of time. And when net force is applied over a period of time, how does that affect the state of a body or object? If we have a net force, that means that is acceleration going to be 0 or something else? So if we do have a net force, that means there has to be a change in the state of motion, right? So there has to be an acceleration. There has to be either speeding up in the positive or negative direction or slowing down in the positive or negative direction. So there has to be an acceleration when we have a net force that's acting over a period of time. So another way of thinking about that is we have a change in momentum. So what is momentum equal to? We have a mass. What else gives objects or bodies momentum? Welcome, Logan. Velocity, yeah. So we have a change in velocity. So we have VF minus VI. Oh, I didn't mean to zero on that. Okay, so that's the key equation from chapter 3, is understanding impulse and momentum. So Newton's second law tells us that the net force is proportional to mass times acceleration. That's instantaneous acceleration. So the instant we have a net force, we have an instantaneous acceleration. So more often in sports, it's force that is applied over a period of time. So it's not instantaneous force. It's a force applied over a time period to either speed up or slow down an object or body. So we can use impulse to decrease momentum. Okay, so we talked about landing from a jump and how we have good landing mechanics. We flex the knees and the hips to absorb the impact. So absorbing the impact would allow us more time, which lowers the average amount of force that our bodies undergo at any given moment. We can also apply impulse to increase momentum. So what Logan does with pitching, what other athletes do in winding up a volleyball serve or a tennis serve, we wind up in order to build force through the kinetic chain over a period of time to maximize momentum as the ball is struck or thrown. So any questions on impulse momentum? Okay, so we left off with one more problem for chapter 3, so let's go ahead and make our participation sheet for today. Okay, so Peter, a 100-kilogram basketball player, lands on his feet after completing a slam dunk and then immediately jumps up again to celebrate his basket. So when his feet first touch the floor after the dunk, his velocity is 5 meters per second downward. So that's important because velocity is a vector, so we need to know what the direction is. When his feet leave the floor 0.5 seconds later, as he jumps back up, his velocity is 4 meters per second upward. So what is the impulse exerted on Peter during this 0.5 seconds? And then question B, what is the net force exerted on Peter during this 0.5 seconds? And what is the reaction force exerted upward by the floor on Peter during this 0.5 seconds? So lots going on over that 0.5 seconds. So we're given 100 kilograms represents his mass. So if you were asked to calculate his weight, how would you do that? Yeah. So we want to know weight. So mass multiplied by negative 9.81, because weight is equal to the force of gravity, which is a vector, so we want to know direction. So that might be a good place to start, would be calculating his weight, because we know that weight is going to factor into both the net force and the reactive force. So that's a pretty easy one to calculate. Probably just do that one in your head. What'd you get for his weight? Yeah, so yeah, negative 981 newtons. So you want to keep that in the back of your mind for now. So we're given two velocities. So how do you decide which one is the initial and which one is the final? So from reading that, can you, what would the 5 meters per second be? Yeah, that would be his initial. So negative 5 meters per second, you'd want to write that down as his initial velocity. And then he comes down and his feet impact the ground, and then he reverses that into the jump to celebrate the dunk, and then on the way back up for the celebration jump, his velocity is positive 4 meters per second. So we could say 4 meters per second is the final velocity. And then we're also given time. Okay, so we're given sufficient information that we can calculate these three things. So let's go ahead and do that. Back over here. So question A, we're asked what is the impulse? So we have time, but we don't really have the net force. So we have to substitute to get impulse. So if impulse, in other words, force times time is equivalent to mass times change in velocity, we can calculate impulse simply by taking what we have and using mass multiplied by the change in the velocity to get the impulse. Because mass times change in velocity is equal to the net force multiplied by time. So we can use either of those combinations based on what we have to get the impulse. So for question A, we're going to take mass, which is 100 kilograms, and we're going to multiply that by the change in velocity. So what was VF? Remind me. Yeah, that's okay. So, yep, it's 4 meters per second minus VI. What was VI? Yeah, -5. Okay. All right, so 100 kilograms times what? 4 minus 5 is going to be, yeah, plus. So it's going to be 100 kilograms times 9 meters per second. So we get 900 kilogram meters per second. Another way of writing that is 900 Newton seconds. 900 Newton seconds is another way of expressing that. Is everybody with me so far? So do you understand why we did minus a -5? Because it was in the downward direction for the initial velocity. Okay. All right, so that's our first answer right there, 900 Newton seconds. Okay, so what's the second question? Net force, okay, so now we want to know the net force. Do we have time? Okay, yeah. And then we just solve for all this over here. So now we can get the net force times 0.50 seconds equals 900 Newton seconds. So how would we solve for net force? Yeah, you gotta just divide by 0.50 seconds. So that cancels out. So what is your net force equal to? How much? 200. Yeah. Okay. with me so far? So, what does question C ask?
What's the reaction force?
Yeah. Reactive force. So, our net force is equal to two things. They're collinear forces. You have a positive reactive force. And what do we put right there? What's the reactive force acts up? Which force acts straight down? Yeah, or what's the force of gravity equal to? Yeah, it's weight. We already calculated weight, so do we have enough that we can solve for the reactive force?
Yes.
Yeah, I think we do. So, I'm out of space here. 1,800 newtons is equal to the reactive force, and what was the weight again? Newtons. Okay, so then you can then solve for the reactive force, right? So you just add 981 to 1,800, so the reactive force is equal to what do we get for our reactive force from the ground during that 0.5 seconds?
780.
So those are our three answers right there. So this is a case where we're just taking this impulse momentum relationship and just arranging it in different ways to solve for what we need. So take what we have and then use this relationship in different ways to solve for different aspects of force. So let you think about that for a minute. Okay, all right. Would you like me to post this on the D2L? I can do that. Okay, so that wraps up chapter 3. Now we're in chapter 4. Work, power, and energy. So we're thinking of work, power, and energy in a mechanical sense. So you've had exercise physiology where you think of energy in a chemical sense, so ATP. So we're talking about the relationship between work and energy in a mechanical way for this class. But we know that energy just changes forms. So the chemical energy, the ATP that we make in our bodies is used to fuel the mechanical work. So chemical energy and mechanical energy is really interrelated. Okay, so work in a mechanical sense is defined as energy transfer from one object or system to another. So from a pitcher to a ball. So the whole wind-up process and delivery. The pitcher is doing work on the ball. So the velocity of the ball as it leaves the pitcher's hand is an expression of the work done by the pitcher. So to calculate work, we need two things. We need force and we need displacement. So think about that. We apply a force, and it has to be a net force, because if the net force is 0, in other words, all the forces acting on a body or object are balanced, then displacement's going to be 0. So if the force you apply, so Annalise said that she did some deadlifts yesterday, and so she applies an upward force on the barbell, and the barbell, due to force of gravity, gravity acts in the opposite direction. So if those forces are equal, so in other words, if the net force is 0, the weight's not going to go anywhere. So we have to have a net force. The reactive force has to be greater than the weight in order for something to change its state, for a barbell to go from rest to being lifted off the ground. So work is expressed in joules, so you'll get Newton meters, but 1 Newton meter equals 1 joule. So just as there was a relationship between impulse and momentum, there's a relationship between work, force multiplied by displacement, and energy. And in a certain sense, these relationships are really talking about the same thing, because with impulse, you're applying a force over a period of time, and over that period of time, as the net force is being applied, there's going to be a change in position. So work and impulse are really interrelated. We're just replacing time with displacement, because net force over a period of time will cause a displacement or change in position, which results in a change in energy. So we need to know the definition of energy. Energy is the capacity to do work. Capacity to do work. So work is energy transfer from one object or body to another. And energy is the capacity to do work. So one of the greatest weightlifters of all time was this Russian gentleman. I don't think I could pronounce his name, but weightlifting is a great example of doing work. So force is applied over a certain displacement. So think about how limb length would affect work. In lab this week, you had to measure your arm length. And so each of you had a load, and you lifted that load for a certain number of repetitions, and each repetition you went your full arm length. So you take 2 people with different arm lengths that are lifting the same load, the one with longer arms will be doing greater work over each repetition. So displacement matters with work. So displacement would be described as the range of motion for a movement. Okay, work can be positive or negative. Positive or negative. So in positive work is equal to force times displacement, and force and displacement are acting in the same direction. Force and displacement acting in the same direction. So concentric muscle actions are a good way to think about positive work. So concentric muscle actions meaning a weight is lifted. So we're overcoming gravitational force, and the weight is being lifted. So the force, the upward force you apply to the bar, is in the same direction as the displacement. So if the reactive force is greater than the weight, the displacement is going to be positive, and so is the work. So negative work. How many of, just weight room terminology, negatives? How many have tried negatives? Yeah, that's where this comes from. Negatives, meaning we're doing negative work. So the force is still positive, but the displacement is in the opposite direction. So here's a picture. Anybody seen this movie, by the way? It's one of the great movies, so you must be a little older.
A little bit, a little bit.
If you haven't seen this movie, it's worth watching. It's great. Over the Top, 1986. Great movie. So to bring this into an example, if you're winning an arm wrestling match, so Sylvester Stallone there beating Bo Hurley, you're winning an arm wrestling match. Is the work positive or negative? Positive, because your force is in the same direction as the displacement. So then if you're losing an arm wrestling match, yeah, but aren't you still, if you're losing an arm wrestling match, aren't you still applying force in the same direction? Yeah, the force application doesn't change, it's the direction that can change based on opposing forces. So arm wrestling or weightlifting both are applicable there. So to go further, with a barbell bench press, the negatives technique. How many have done a bench press with negatives? Okay, negatives. So usually you have a little more weight on the bar than what you can lift. So you have a spotter there to help you, and so you're lowering the bar towards your chest. What direction are you applying force to the bar as the bar is being lowered to your chest? Are you pulling the bar towards your chest? Or are you allowing it to go to your chest? There's a difference. You're allowing the bar to come down, which means your force is in the upward direction, but the force isn't sufficient to overcome the weight, so the displacement is in the opposite direction as your force. That's another way to think about negative work. So, sports applications to consider. Why is a wind-up or a backswing important in throwing and striking activities? So sometimes we call this the preparatory phase. The agonist muscles undergo a pre-stretch. And because of this rapid pre-stretch, these agonist muscles are able to accelerate and contract with greater force and power. So preparatory phase is really important. The agonist muscles undergoing a stretch prior to the movement phase. From an injury prevention standpoint, why is a follow-through important in throwing or striking activities? So think about impulse, momentum, work, energy. So if we're absorbing force as in a follow-through, absorbing force over a larger displacement, which is what the follow-through is, we're slowing the arm down over a longer displacement, which reduces the energy that our joints have to deal with at any given time. So it ties right into that impulse-momentum relationship. Another factor, most major league pitchers tend to be taller and longer limbed than other players. Why might this be an advantage in pitching? So Randy Johnson, 6'10". So why would a taller, longer limbed pitcher have an inherent advantage? Or displacement. So they're able to build the net force over a longer displacement before releasing the ball. So, okay, so negatives. Force and displacement are in opposite directions. So the bar is going in this direction, and we're applying an upward force, but not sufficient to overcome the weight. So some of my other classes, we talk about this concept of being stronger during eccentric type actions. So we can lower a lot more than we can lift, 30 to 70% more, in fact. So there's some science behind this, and here's an article. Why are muscles strong, and why do they require little energy in eccentric action? So that's the other thing about eccentric actions. Not only are we stronger, but they're also more efficient. So we expend less energy during eccentric actions versus concentric actions. So it has a lot to do with the elastic properties of muscle, where we're not breaking down ATP, we're just using the elasticity of muscle to lower the weight or lower our body weight. So practical application, pull-ups serve Pretty hard exercise, probably one of the hardest exercises to do well. Takes a long time to learn. So we can build into those slowly by doing negatives. So we can give ourselves a boost up to the bar there, and we can hold for a period of time, and then we can lower slowly to build our strength that way. Pretty soon, after a while, when you've developed your eccentric strength, you can then discover that you're able to lift your body weight too. So it's a good way to build into pull-ups. So this just kind of illustrates the point. When we do traditional repetitions, the eccentric phase is really submaximal compared with the concentric phase. So something to consider if you have equipment or a really creative mind, you can somehow change the eccentric part to be a higher load, and then the concentric part a lighter load, which would fit how the muscles work. So another practice problem for you. So a therapist is helping a patient with a PNF hamstring stretch. What does PNF stand for? Yeah, there you go. That's what, Levi said, proprioceptive neuromuscular facilitation. He pushes on the patient's foot with an average force of 200 newtons. The patient resists the force and moves the foot 20 centimeters in the opposite direction towards the therapist. How much work was done during this stretching exercise? So let's assume that the displacement was in the positive direction, just to make it easier. So let's put the force and displacement in the same direction here. So work is equal to Newton meters. So how would you convert 20 centimeters to meters? Just move the decimal, right? Just like we did in lab this week. So it'd be 0.2 meters times 200 newtons. What'd you get? How many joules? Yeah, 40 joules is right. So just a simple example there, 40 joules. So remember, Newton meters is joules for work. Energy is also expressed in joules. Okay, so range of motion strength training, very, very important. So we don't ever want to increase the load when we're not prepared to lift it through a full range of motion. So this would especially apply to the squat exercise, where we see a lot of limited range of motion in order to lift a greater load. And so I've seen Logan squat, and he squats with heavy weight, but he always goes through the full range of motion. So he's to the point where the crease at his hip at the bottom of each repetition is below the top of his knee, which would in powerlifting would be a legal squat. That would count as a legal squat in powerlifting. So we really want to focus more on range of motion, hip mobility, ankle mobility, because our muscles adapt in terms of strength, in terms of size, in terms of power when we lift through a full range of motion. Olympic weightlifters have tremendous range of motion, and that's because the heavier the weight, the more difficult it is to get it off the ground. And so as they are doing their max lift, they have to get it as high off the ground as possible, which isn't very high, and then they have to get underneath it. So you have to have tremendous quickness in order to be faster than gravity, because as soon as that weight goes up, what is gravity doing? It's going to accelerate it back down. So you have to be quicker than gravity to get underneath it. And then you have to have the stabilizing strength and the mobility to catch it and then stand up with it, which Olympic weightlifting is just a great way to develop overall athleticism. Best way to lift, in my opinion. It takes a long time to do it properly, though. There's a very high skill component. So a lot of times we start with just doing deep front squats, because you've got to learn how to front squat like this in order to be effective at Olympic weightlifting. Then we might do jumps off the floor where they're doing kind of a jump shrug action. So going from that deadlift position into a jump shrug, and then eventually we work into a high pull, right? How many have done high pulls? Okay, and then we go from a high pull into a catch. So there's a progression involved. It takes a while to learn properly. So here's a pull-up example. So why are we placing an X over here and a check mark right there? Same person. Yeah, so can you see just the little subtleties in technique? Certainly the chin is above the bar here, but we're not getting that full retraction here at the top. So just those little subtleties make a big difference in your results, making the most of every single repetition. Okay, so evolution of technique. Looking here at this picture from the early 1900s, that was a shot put, and then modern times, the shot put. So you're in a circle. You can't go outside the circle. So if we look at force and displacement, in other words, you've got to do work on the shot in order to project it as far as possible. So if you have a limited space in which to move, you've got to be more effective within that limited space. So what's the difference between this and this? So early 1900s, you started your shot facing the same direction you're going to throw, so you weren't able to build force over as long of displacement or as long of time. Whereas here, this is actually facing the opposite direction from where the shot is going to be projected. So working within a limited space to increase the amount of time and displacement the shot is going to go through before being released. It relates to impulse momentum because this allows more time to build force through the kinetic chain before the shot is released. So, okay, so energy, work and energy, related concepts. So work is the transfer of energy. Energy is the capacity to do work. So we have a couple of different types of energy that are relevant here. First, we have potential energy. So what does that word potential mean? Have we used it yet? When you have something that's potentially there, you haven't used it. So it's not energy that's being used. It can potentially be used. So we have a couple different types of potential energy. First one is strain potential energy. So what does that word strain mean? If you think about a rubber band, what does that word strain mean? We think about our tissues in our body that undergo strain or deformation or change in shape or stretch is another way of thinking about it. We have tendons, and our tendons have a lot of elastic type fibers. So our tendons are a lot like rubber bands that stretch and then recoil to give us more force. So strain potential energy is equal to 1/2 times the stiffness of the material. So this is just a constant, kind of like the coefficient of friction that describes the stiffness of the material. And then X is the amount of stretch. So because X is squared, the amount of deformation or the amount of change in shape is the most important factor. So speaking of our bodies and our tendons have a certain amount of stiffness. And when we stretch, tendons undergo a change in length. So this X represents a change in length. Can tendons vary in how stiff they are? Can tendons vary in how springy they are? Yeah. So over the last several years, it's been discouraged to do excessive amounts of static stretching just before jumps and sprints. What is static stretching? So kind of the traditional stretching you see most people doing in a recreational setting. It's just sitting, and then you take a joint to the limit of its range of motion until you feel that stretch in your muscles and tendons, and then what do? I guess it's the point of they say mild to moderate discomfort. Then you hold it for a period of time, right? That's static stretching. So with static stretching, we're lengthening out this tendon, and we're putting some slack in that tendon. What is the function of a tendon? What does it do? It transfers what from muscles to bones? Tendons are like bridges. They transfer force from muscles to their attachment point. That's how we move. So a muscle contracts, and that pulls on the tendon pulls on its attachment point, and that's how our joints rotate. So imagine getting ready to do a sprint or a jump with maximal effort, doing an excessive amount of static stretching beforehand, and now you've got a nice slack tendon, which is nice from a health standpoint. But how springy is a slack tendon? Not very springy. So we've taken the spring out of our tendons, which is really important if we want to jump high and run fast. We want tendons to have a little more spring. So that's why it's contraindicated now to do a lot of static stretching before a sprint or a jump. What would be a better way to warm up prior to a sprint or jump other than static stretching? Yeah, dynamic. So we're warming up muscles while preserving the spring quality of our tendons. So when would be a proper time then to do static stretching? It's just the timing thing is the issue. Yeah, afterwards. That's a better time anyway because our muscles are all warmed up and you can get into a better range of motion anyway. So if a tendon has a lot of slack in it, it takes more time to take up that slack to pull on that attachment point. And so your movement velocity is going to be slower. So then you might ask, well, what is considered excessive? So there actually has been research done on what is considered excessive static stretching, and it would be in the range of about 90 seconds. 90 seconds just before a sprint or a jump would be considered excessive. So we want to stick with the dynamic warm-up methods, and then static stretch afterwards is a good idea.
Is there like a time frame of when, like let's say you're sprinting in the afternoon, are you okay to static stretch first thing in the morning?
It's a window of about 15 minutes.
Oh, okay,
So once a tendon is kind of all lengthened out, it takes time for it to creep. It will start to creep back to its original length and start to get that spring quality back, but it takes a little bit of time.
Okay.
So you'd be okay in the morning if you wanted.
Okay.
In the afternoon, just do your dynamic and so. So I have a present. We'll watch a video on that maybe next class. Okay, so you can use bands for all kinds of things. How many of you use bands for different things? Look around. Yeah. Okay, so there's different colors. What do the different colors represent? Different. Yeah, resistance, which would be equated with stiffness, right? So a stiffer band probably means there's more material, so it's thicker. same material but more of it would be stiffer. And so you choose a color according to the stiffness of the material, and then you can, the more you change the length of the band, the greater amount of resistance that you get. So we can use bands for all kinds of things. This is probably one of the most important stretches because most athletes have pretty tight hip flexors. And if any of you identify with that, really tight hip flexors. So we can really use bands in very practical ways. All of these methods here are great ways to loosen up the hip flexors, because if the hip flexors loosen up, the muscles on the backside, the gluteus maximus, tends to be more facilitated. So a tight muscle on one side, especially if it's chronically tight, tends to turn off muscles on the opposite side. And so if we're a sprinter or a jumper or really any athlete, we don't want our glutes to be deactivated because our hip flexors are overactivated, if that makes sense. So hip flexors are also interesting because they attach right to your lumbar spine. So if they're tight, what's your lumbar spine going to feel like? It's probably going to be, you're going to have a lot of low back pain because the origin of those iliopsoas is right on the lumbar spine. So this is kind of a good thing to do every day, not only to ensure good glute activation, but also low back health. So just another application of strain energy. Any pole vaulters in here? One of my daughters is a pole vaulter at West, so she's getting ready for the season. But apparently the pole vaulting materials have evolved over time, just like everything else. So it began with ash, and then bamboo, and then aluminum, and today fiberglass. So if we think about the flexibility of the pole, and I don't know what the rules are. I'm sure there's got to be some regulations on what kind of pole you can use. There's probably some poles that would just throw you up 20 feet.
It has to do with how much you weigh. So like if, I know there's poles that have labels, so like 140, and then if the pole says 140, I don't think you're allowed to use it if you're less than 140.
Yeah, so yeah, it would seem there'd have to be some pretty strict rules. Pole vaulters are also generally pretty fast people. So think about energy transfer. Why would you want to do some sprint training if you're a pole vaulter? Yeah. Yes. You're exactly right. So all that horizontal velocity is transferred into vertical displacement on your takeoff. So if you have two pole vaulters that are equal in skill and all other aspects, if one of them is faster, you're going to be a better vaulter just because of that potential for energy to transfer from horizontal to vertical. So the other type of potential energy, so strain potential energy, 1/2 kx squared. The other type of potential energy is called gravitational potential energy. So gravitational potential energy is equal to mass multiplied by gravitational acceleration multiplied by height. So you have to define what the surface is. So typically it's just the ground. The ground is the reference from which you are measuring height. Okay, so now we get to kinetic energy. So two types of potential energy, strain and gravitational, and then kinetic energy. So kinetic energy is energy due to movement. So formula is 1/2 mass times velocity squared. So it's similar to the equation for momentum. Momentum was mass times velocity. So the more momentum an object or body has, the more kinetic energy will be expressed through that object or body. So the greater capacity to do work with more kinetic energy. So in a pole vault, think about it, as you are doing your approach, all of the energy is kinetic. So the faster you are, the more kinetic energy you'll have at the takeoff point. So velocity is the most important factor. So then you get to the end of your approach, and all of that kinetic energy is transferred into potential energy. So whatever amount of kinetic energy you have, you want to transfer into potential energy, because that's going to determine how high above the ground. So just to illustrate a simple example, inverse relationship between gravitational potential energy and kinetic energy. Okay, so we're at the top of the ski jump, and we have a certain amount of kinetic energy and potential energy. Why is kinetic energy 0 at that point? Not moving, yeah. You have to have velocity to have kinetic energy. So all of the energy at this point is potential energy, gravitational potential energy. So the height above the ground. So then starting down the hill, and we get halfway down the hill, so we're building in velocity. The height relative to the ground is decreasing, and so now we have 20,000 joules of kinetic and 30,000 joules of potential energy. And now we're down here, and so we can see kinetic energy is building, potential energy is decreasing, and we're off the jump, and then at the same height here, the amount of kinetic and potential is the same due to the height, and landing here, at the instant of landing, all of the potential has now transferred into kinetic. So just to show the interchange there with that. Okay, so let's work this problem. Shayna is pole vaulting. At the end of her approach run, she has a horizontal velocity of 8 meters per second. So pretty fast. And her center of gravity is 1 meter high off the ground. If Shayna's mass is 60 kilograms, estimate how high she should be able to vault if all her initial kinetic energy and initial potential energy are converted to potential energy. What is the kinetic energy final equal to? So in other words, when she gets to the very top, where she's at that point of her maximal height, what is her kinetic energy final going to be? She's not going up, and it's the instant just before she starts to come back down. It's kind of like our projectile problems. So because her velocity at the peak height is going to be 0, she can't have any kinetic energy when she's at her peak height, hopefully going over the bar. So the kinetic energy is 0. So then what we can do is just look at the potential energy final, because that's going to tell us how high she goes. We're given a little bit of information, potential energy initial. What is her initial height of her center of gravity? Yeah, 1 meter. Okay, so that's relevant. And then just before takeoff, she has some kinetic energy due to her movement. Ooh, board is really sensitive. And we're also given her mass. Okay, so let's go ahead and set this up. I want you to write this equation down, potential energy final. Okay, and what is potential energy equal to? Gravitational potential energy. Yes, mass times acceleration due to gravity times height. Okay, now, energy is a scalar quantity. It's not a vector. So what's the significance of that? Not a vector means what? It doesn't need direction. So for gravitational acceleration in this case, I want you to use just 9.81, not negative 9.81, 9.81, because we're going to be solving for height above the ground. So on one side of the equation, I want you to write mass, 60 kilograms, times 9.81 meters per second squared, times h. That's what we're solving for, is the final height. So that h on this side is what ultimately what we're trying to get. How high above the ground? Hey, Brian. So PEI, so that's going to be the same. It's going to be 60 multiplied by 9.81 multiplied by its initial, so it's going to be 1 meter. That's the initial height of her center of gravity. Okay, so then we're adding that to initial kinetic energy. What's the formula for kinetic energy? 1/2, good, Caitlin. So 1/2 mass times velocity squared. So 1/2, 60 kilograms times 8 meters per second squared. Don't forget to square that. Okay. So once you've got all that written down, I want you to draw a great big line under all of this right here. Great big line under all of the PEI stuff and all of the KEI stuff. How can you solve for h on this side of the equation? What do you need to do to solve for h? How do you get h all by itself? All right, let's go out here. Okay, so we got, help me out here. So mass is 60. Times 9.81 meters per second squared times height. We don't know what that is. I'm going to have to write small for this other side. So PEI is going to be 60 times 9.81 times 1.0 meters, and I didn't do a very good job, did I? Plus 1/2 60 kilograms times 8 meters per second squared. Okay. So let's work on this side to start off with. What's 60 times 9.81? 588 kilogram meters per second squared. Times height. Okay, let's work on this side now. Let's start with this right here. So this is also going to be equal to what? Yeah. So 588 kilogram meters squared over second squared. And then what are we adding to it? What's 8 squared is 64 times 64 times 60 is what? Times 0.5 is what? 1920, so just gonna get rid of that, so. Okay, so how do I solve for height then? Is it too easy a question? One of those scenarios? Yeah, I remember. Okay. So then what are you left with for your height? Mm-hmm. Okay. How are we doing on time? 9:40. Okay. I think that's probably about enough for today. Let you guys go home. Have a good weekend. So, finish chapter 4 on Tuesday. Remember, no lab next week due to President's Day. So, hope everybody does well. Stay safe out there. I'll see you next week. Let me collect your participation sheets for today. Oh, thank you. Thank you.
How cold is it outside? Do I need a coat?